announce our today's speaker, who is Julia Böttcher from London School of Economics. She did her PhD in 2009 at the Technical University of Munich with Arno Staras. And then after a couple of postdocs, she started at LSE, where she remained until now. Now she's associate professor. And maybe also let me just mention that in 2018, she was one of the recipients of Alcrson Prize for their work on chromatic thresholds in graphs. So please.
Thank you very much. And thank you for the invitation. I noticed when preparing for this talk that actually I didn't give a talk in a while. So I'm a bit out of practice, but I hope I managed nevertheless. Thank you for having me, not in Warwick, unfortunately, in these funny times, but online here. And what I'm going to talk about today is joined with my colleagues from London School of Economics, Olaf Parczyk, Amedeo, Sgueglia, and Jozef Skokan. And most of the slides are also stolen from them shamelessly, but any errors are, of course, mine. Okay, so what am I going to talk about today? Oh, so by the way, I have the chat open, but I noticed when teaching that I'm not very good at monitoring that. That's why I told Ramanujan to stop me whenever something comes up in the chat. But if you want to interrupt me, that's also perfectly fine. You can just unmute yourself and ask a question if you feel confident to do that. Okay, good. So what I'm going to talk about today is triangle factors in randomly perturbed graphs. And of course, I should say what all this means and do the definitions. But what I'm going to start with is some kind of background which motivates the problem. And this research area is actually motivated by two different areas. And I will start with the first one, which just concerns minimum degree thresholds in graphs. And here, this is, of course, one of the classical problems in extreme graph theory. And we have some dense graph typically. Then what is the minimum degree threshold for this graph so that certain subgraphs start appearing? And what we usually think of here is that these subgraphs are spanning. Yeah? And I'm just looking for normal subgraphs, so not induced, but just some subgraphs. And we want to know when we can force them as a subgraph of some given graph G, which has a minimum degree condition. And of course, the classical result here is the theorem of Dirac, which says if I have minimum degree n/2, then I can certainly enforce a Hamilton cycle. And that was maybe the first theorem of this style, but then there were lots of others, and I'm not going to mention many of them, but here's one that is relevant for this talk, and that concerns perfect KR tiling. So what's a KR tiling? Well, I just have vertex disjoint copies of KR. So for example, if R is equal to 4, I would have K4, and then I have vertex disjoint copies of these KRs spanning all the vertices of my graph. Well, as long as the number of vertices is divisible by R, if not, then maybe you have some vertices uncovered, but this I'm going to ignore here now in this talk. And I will always assume that the number of vertices is really divisible by this little graph that we want to find a tiling of in my graph. Okay, and then the classical result of final and summary says, if I want to find such a KR tiling in the graph, what is the minimum degree that I need? It's 1 minus 1 over R times n. So it only depends on this R on the number of vertices in my clique. And at this minimum degree, I get this graph as a subgraph. And then of course, there have been lots of other results in this area where people looked at more general graphs, like for example, powers of Hamilton cycles, which I don't want to define here now, or even more general graphs. So this is really a rich sub-area of extreme combinatorics. And there are also still some open problems, like let's say the famous Waller-Eldridge-Catlin conjecture that has not been resolved so far. But this is a different story, and I don't want to go in that direction today. But here's one more result that actually also have this flavor from Kühn and Ostos in 2009. So they asked, now what if I don't want to look at KR tilings, where the little graph that I'm tiling with is a clique, but if I have more general sum graph H that I want to tile with. And they determined the minimum degree threshold for this, for finding this subgraph. And now this minimum degree threshold is something that depends on some parameter chi star of H, which either is the chromatic number of my graph H, or it's something more complicated, which is called the critical chromatic number. But let me not even go there. So things get more difficult when I ask for these H factors, but it is known what precisely this threshold here is. Okay, so that's maybe the message that this should tell you. Okay, so that's minimum degree thresholds in graph, which is kind of the first area that motivates the research I want to talk about. But then the second motivation is thresholds in random graphs. So, and what we are looking at here is the normal binomial random graph GNP, where I have n vertices and any edge appears independently and with probability p, where p can be some parameter that depends on my number of vertices n, of course. And we also know that we say that if we have some property A, so in our case, these properties will just simply be finding these subgraphs of graphs, then we say that we have a threshold for this property if, well, whenever we are below this threshold, then we with high probability don't have this property appearing. And if we are above this threshold, then with high probability, we have this, we are in this property. Okay, we know that these thresholds exist, and as long as we have monotone properties, and of course the properties that we are interested in, they are monotone properties. So a property is monotone if we just talk about graphs, if they are closed under the addition of edges. Yeah, and since here we just talk about subgraphs and not induced subgraphs, then we are talking about monotone properties. Okay, so that kind of was just a very brief reminder about thresholds in random graphs. Now, concerning the particular problems that I'm interested in, what is known here? So again, so we have our random graph GNP, and we want to know what is the threshold so that it contains a given spanning subgraph H. Now, of course, since this subgraph H is spanning, and when we look at GNP, then always we think of n going to infinity. It's a little bit misleading that I just write one graph H here. This is, of course, a family of graphs, right? So for every n, I have a different graph H here. Okay, so what do we know about this? Let's go with the Hamilton cycle example again that we also started in the previous topic with. So this is, of course, also one of the classical results of the area proven by Böttcher and independently by Korshunov, that the threshold for when some Hamilton cycle appears in GNP is log n divided by n, right? Okay, and if we look at perfect KR tiling, then that's the famous theorem of Johansen, Kahn, and Wu, which determined the threshold for this property. And the threshold is this here. So we have n to the minus 2 over r, and then we have some additional logarithmic factor that we need because we want to find copies of KR which really span my whole random graph. Okay, Johansen, Kahn, Wu, in fact, actually did more. They did not only determine the threshold for KR factors, they looked more general at H factors, put forward a conjecture when for H tilings, when we should find them, so what should the threshold be for H tilings. They proved this conjecture when H is a strictly balanced graph, which again, I don't want to define here now because also that is a different story that I don't want to tell today. There were some more graphs H for which this conjecture was proven by Gerke and McDowell, but there is still some graph H for which we don't have a proof yet of what is the threshold for finding H factors of these graphs. Okay, so again, and of course, again, in this kind of results of this type, there are many, many more, and there has been lots of progress in recent years. There are also still some open questions and things we don't understand very well. So this is a rich theory, and again, something which I have to ignore many, many of the details in order to come to the topic that I want to focus on in this talk today. Okay, so we have now kind of these two background topics, extremal graph theory for spanning subgraphs, and then spanning subgraphs of random graphs. And what I now want to do is I want to put them together, and that motivates the study of so-called randomly perturbed graphs. All right, so what is the problem here? So when we have a random graph, then one other way of thinking about this random graph is the following. I could say, okay, I start with an empty graph, and now I start throwing in some edges, and I do that randomly. So that, how many edges do I throw in? Well, as many as I would roughly get when I had an expectation when I had a random graph G and P. Now, what I want to do when I talk about randomly perturbed graphs is something similar, but I don't want to start with the empty graph. I rather want to start with some graph which already has some density. And then I want to throw in random edges. And then I want to say, okay, what does the object that I get out of this look like? And in particular, in the problems that I focus on today, I want to ask when does the resulting graph contain a given spanning subgraph H? And here's a little bit more. So that should be the intuition. And here's a little bit more formal definition that was coined by Woman, Fries, and Martin, who introduced this model. Yeah, so they said, we take some alpha, which is some constant in 0, 1, and then we have some graph G alpha, and that has always n vertices, and it has minimum degree alpha n. So it has a linear minimum degree, and this alpha determines what fraction this minimum degree is of the total number of vertices. So I start with this G alpha, and that's really in some sense adversarially chosen. And then on top of that, I put a random graph. So I take the union of G alpha with a random graph. And of course, this random graph also comes with a parameter, and that's just simply my edge probability as before. Yeah, and this I then call a randomly perturbed graph. Okay, and now once I have this definition, then I can revise the problem that I stated above as follows. So now if we have this randomly perturbed graph for some given alpha, then we can ask, what is the threshold? So how should I choose my P so that this object here with high probability starts having a given spanning subgraph H? Okay. And this problem now really has kind of a number of different facets, or there's a number of different ways in which one could view it. So either you could think of alpha being small, so that means you have some dense subgraph G alpha that you start with, but the minimum degree condition is really small. So you have a very weak minimum degree condition on this graph. And then you can ask, okay, if I have such a small minimum degree condition, how many random edges do I actually need in order to get the spanning structure that I want? Yeah. So here we would think of, so here we could also think of saying, okay, in the random graph, I have a certain threshold when my H starts appearing as a subgraph. But now I add some dense graph on top of this, and this should somehow help my random graph, maybe having the property earlier. So you could ask, if I have this for a very small alpha, this deterministic graph on top, then how does that change my threshold? Yeah, so that would be one question. And indeed, that was a question that was studied for a lot of different properties. But then you could also ask at the other extreme, when you think of a very small p, and by small p, usually one would think of some p being just constant divided by n, which would mean that in expectation, you only add constantly many random edges. Yeah, and then you could, of course, ask, okay, so I'm allowed to add some constantly many random edges. Now, how does that change my minimum degree threshold of my dense graph for having the substructure that I have? Yeah, so if you want, you can see that as some analog of maybe something like smooth analysis, yeah, where you say, okay, we don't want to really look at our worst case input, or in our case here at our worst case extremal example, but we want to smoothen that a little bit by allowing just a few random edges. Yeah? And again, that is a question that has been studied for quite a number of different objects. But what is also clear is that these kind of two phenomena that I just talked about now are just the two extreme points of some kind of a wider spectrum, right? So you could imagine the parameter alpha, which determines the minimum degree, to go from being very small, then all the way to where it would be for the extremal result. And when you do that, the number of random edges that you need to add, that will of course change. And so you have some kind of evolutionary behavior here, and you could aim at studying this whole evolutionary behavior. And that's indeed what I want to be interested in today. Okay, but before I come to these results that I'm interested today, a little bit more background of some things that have been studied for randomly perturbed graphs. And here again, there have been lots of results in the last 10 years, and I'm going to ignore many of them. And I'm just going to focus on a few here. So sorry if your favorite result is not mentioned here. Okay, but before I come to that, let's just kind of make sure that we all understand what we have to prove or to show when we want to solve one of these problems that I just raised on the previous slide. So we have some minimum degree given that our deterministic graph has, and we want to know now for this minimum degree, what is the threshold that I need, or the number of random edges that I need, so that my substructure starts appearing in my randomly perturbed graphs. And as usual for random graphs, also here that kind of consists of two things, that there's some zero statement and some one statement that we have to prove. But since we talk about randomly perturbed graphs, they are now a little bit different, right? So the zero statement would mean that when my probability is below my threshold that I want to prove, then I find some adversarial graph with minimum degree alpha n, such that when I add the random edges on top of it, then asymptotically sure, almost surely I don't get the structure that I'm looking for. And for example, I don't get a perfect H-tiling if that's what I'm looking for, right? On the other hand, in my one statement, where I'm below my threshold probability, then I really need a statement for all possible different minimum degree graphs G alpha, that asymptotically almost surely my substructure starts appearing. Yeah, so that's maybe a bit different. So in the zero statement, I just need that there's one counterexample, and in the one statement, I need to show that for all these graphs, I get the property that I want. Okay, now here is the result that started the area by the aforementioned paper of Roman, Fries, and Martin in 2003. The property that they studied was Hamiltonicity. So they looked at what happens to my threshold when I'm allowed to add some deterministic graph G alpha to my graph GNP. Yeah, and it turns out that what they actually proved is that, so we know the threshold for Hamiltonicity is log n over n. And what they proved is, if now I have in addition this minimum degree graph G alpha for alpha bigger than 0, then my threshold probability goes down by a logarithmic factor. So I don't need this logarithmic factor anymore, but having p bigger than equal than some constant over n is enough. So I add in expectation a constant number of random edges to my minimum degree graph G alpha, and here alpha can really be any constant that is bigger than 0. Okay. Now, if we look at this in terms of this evolutionary behavior that I talked about just a little bit ago, then that would kind of mean the following table. So if alpha is 0, which means I only have the random graph, then this was my threshold probability. And we also know that if our minimum degree is bigger equal than 1/2 times n, then I don't need any random edges to get a Hamilton cycle guaranteed, right? And now what they proved is that in between, my threshold probability is n to the -1, so I save this logarithmic factor here. Okay, and this phenomenon of that you can save a logarithmic factor in the threshold probability, that was a phenomenon that was then afterwards studied for a good number of other properties as well, and that kind of behavior was also observed for many other properties. But then people also start to find some properties where you're not able to save this logarithmic factor in general, and also some properties were found where you can save more than a logarithmic factor. All right, but again, that's a different story, and I don't want to go there. Instead, I want to go to perfect tilings because that's the topic of my talk. And here, a recent paper of Balog, Treglown, and Wagner studied this problem. And if I just phrase their result for that they established for KR tilings, then they showed the following. So they showed that for this probability here, if you have any alpha which is bigger than 0, then your randomly perturbed graph will contain such a KR tiling. Now let's try to put that into context. So the threshold for KR tilings, which comes out of the Johansen-Kant-Wu result, is this here. So we have indeed this probability n to the -2 over r, which is the same as here. And then again, we have this logarithmic factor here. And so what they showed in effect is, again, the same phenomena is that if I add some minimum degree graph G alpha, then I can save this logarithmic factor, right? And in this table, what I wrote here is just, again, the extremal result coming out of the Heinald-Semeredi theorem, that this is the minimum degree threshold when without any random edges, I get a KR type, okay? And indeed, they proved more. They didn't just consider KR tilings, they looked at H tilings and established some corresponding results there, but let me not mention this in detail now. They also were able to argue that as long as alpha is smaller than 1 over r, then saving this logarithmic factor is actually all that you can do. But what they asked then is what happens when alpha is bigger? So what happens when alpha is between 1 over r and this 1 minus 1 over r here? What happens to the probability threshold then? And this is a problem that was then also picked up by Yihan, Patrick Morris, and Andrew Treglown in a more recent paper where they study more precisely what happens in between these values. And they were able to give some very good bounds here. So, and let me maybe first look at what the results that they are in the case of K3 tilings. So they look at general KR tilings, but here's what their result says for K3 tilings. It says, okay, there are some intervals here, right? So this was the purely random result. This was the purely extremal result. And then we had the jump from this threshold probability to the same without the logarithmic factor, which should hold up to smaller than 1 over 3. And then there is another interval going from 1 over 3 to this 2 over 3 here, where indeed the threshold probability gets better. So there I just have constant divided by n here as this probability, okay? And so that's so I get some kind of jumping behavior for these probabilities. First, I only save this logarithmic factor to get here, but then it jumps to this value before it jumps to 0. And when I go to higher values of r for KR tilings, then I have more of these intervals, right? So what I get is I can choose any k between 2 and r, and then my alpha is, as long as my alpha is in 1 minus k over r and 1 minus k minus 1 over r, so I have one of these intervals here, then this k, this parameter k, is what determines this threshold probability that I get for getting a perfect KR tiling in my randomly perturbed graph. Okay. Good. So they answered this question, but of course one question remained here, and that was what happens in these boundary cases. Yeah, so here the alpha, for example, for this K3 tiling, the alpha is really here in 0 in the open interval 0 and 1/3, and then here I'm also in the open interval 1/3, 2/3. And the question is what happens at the precise value alpha being equal to 1/3, and this they couldn't answer in general. And of course for K3 tilings, this is really the only question that is left. Yeah, if we want to precisely determine this evolutionary behavior here, then we know for all values of alpha what the threshold should be, but this value 1/3, and therefore that was kind of what we started out working on when we worked on this type of problems. Okay. So, okay, so what should the threshold be at this value alpha being equal to 1/3? Now it turns out that 1/n, which is the right answer precisely after we are at 1/3, is not enough. So that's not enough to get a perfect triangle tiling. And the reason why this is the case is here. So if you just take a complete bipartite graph with n/3 vertices in one of your partitions and 2 n/3 vertices in the other partition, then that has your required minimum degree. So that would be your graph G 1/3. And now you want to find you are now allowed to add in some random edges, and you want to find a triangle factor in this graph. Now, what is the difficulty here? The difficulty is, of course, that just because of the way that the sizes of these partition classes are, all your triangles should better look like this, that they have 2 vertices over here in this part, and then 1 vertex over there in this part. Yeah, otherwise we would need to find a whole triangle in here, and that certainly wouldn't be possible at this edge probability. Okay, but if I want to have all my triangles looking like this, then what does it mean? It means that over here in this part, I need to get a matching, right? And for getting a matching, using just random edges in this part, then having this probability is not enough. And that's why I certainly need at least log n/n log n/n in my probability in order to get this triangle factor. Okay, and what we prove is that this is indeed the answer. So if my alpha is 1/3, then having precisely this edge probability does indeed give me a triangle factor. And okay, so meaning that on the one hand, we fill this gap that was left here. Now, do we do it also more generally for KR factors? Well, the answer to this here is no, and I will explain later in my talk why the answer is no. But we do a few things more generally and in addition to that. And that's kind of what I want to explain now. So we prove something more. So first of all, in our proof, and I will come to that, I will kind of detail that a little bit in a while, we naturally have to distinguish into some extreme case and some non-extreme case, which is something that happens very often when one wants to prove some exact extreme results. Therefore, I will have some case where my graph G alpha with the minimum degree is close to some extremal graph, and I will have some case where I'm not close to some extremal graph. Now I will say a little bit more in a second what it means to be close to this extremal graph, but what you should think about, what it should roughly mean is that I'm close to this extremal graph. And what more precisely this means, I will say in a second. Okay, good. Now, in the case that I'm not close to this extremal graph, we can prove a bit more. We can namely say that, now actually we don't need probability log n/n anymore, but we just need linear probability. So that's one thing we are able to say. But in addition, we don't just look at this case for alpha is equal to 1/3, but we can look at some general alpha, which is okay, not too small and smaller equal than 1/3. And then say, okay, now of course, if we have some smaller alpha, we won't find a perfect triangle tiling anymore, but we will at least find alpha times n many disjoint triangles. Yeah. So somehow we have some scaled version of our result where my minimum degree is smaller, but then I also get less triangles. And this is, and the scaling here works linearly, right? And this is actually something which is very natural, because that's also something that happens in the Heinald-Semerelli theorem, where again, we got the minimum degree threshold for when some KR tiling appears, but actually again, they prove more. They say, okay, if you don't want a perfect KR tiling, but just want a KR tiling covering X% of your graph, then they can also tell you what is the minimum degree that you need. And that's again, a linear function. Okay, good. So we get that, but on top of that, we get even a bit more. So now for a second, imagine again that alpha is equal to 1/3, which was our case that we were originally interested in for getting a perfect triangle factor. Now we are, so if alpha is 1/3, then we don't really need minimum degree 1/3n in this non-extremal case, but we can go a little bit below 1/3n. Yeah? So we can subtract here this gamma, which is just some very, very small constant. So our minimum degree can be a bit smaller than 1/3n. We only have these constantly many random edges, and we still get a perfect triangle factor. Okay, so that's some of the things that we get in addition. Here is another result that follows from the things that we prove. And that says the following. So now I'm in the general case, so I could be extremal. So I certainly need probability C log n over n to get the object that I want. And I have an arbitrary graph G that I add on top of here. And I want to find disjoint triangles again. And the number of disjoint triangles that I get in this scenario is, again, either I get a perfect triangle factor, or I just get delta of G many disjoint triangles if that is less. And here in this result, the interesting thing is that this delta of G, I don't insist anymore that this is linear, but it can really be any number. Yeah, and kind of the funny thing is that we didn't originally set out to prove a theorem of this type, but it turned out that in our proof, we actually need something like this. We need something like this, where the number of triangles is not necessarily linear anymore. And I also have a very, very small minimum degree here. So that's really something that came out of our proof, but I still kind of like this result very much because it allows for general minimum degree. Okay, and then moreover, also in this result, I don't need the log factor if I'm not close to the extremal graph. Good. All right, so let me spend a few minutes trying to say a little bit about the proofs of these things, and then I'm going to look at the case of KR tilings and also at some more open questions that naturally come after this book. Okay, so some glimpse into the proof. So here is some lemma that we use. And this lemma talks about super regular pairs. If you don't know what a super regular pair is, then you should just think of a random looking graph with some minimum degree condition. Okay, and this lemma that we are using in our proof says the following. If you have 3 vertex sets, U, V, and W, and now in my lemma, they are all of size n, so they are all the same size. So here is V. Here is U and here is W. And in addition, I have the property that VU and VW, these are some super regular pairs. And the graph between U and W, on the other hand, that is a random bipartite graph. Yeah, with this edge probability log n over n that we are interested in. Then that's enough to find a triangle factor in this graph. Okay, So this lemma is not very difficult to prove, and one can use some standard technology in order to prove it. Now, why is such a lemma useful for us? So in the case that we are looking at the that we are close to the extremal graph. So now, of course, I have to tell you a little bit more in detail what I mean to being close to extremal. So beta close to extremal. Now here means that my graph looks as follows. I have two vertex sets A and B. And they're more or less of the size as they would be in the extremal case. Yeah? So I have 1/3 and then plus minus beta times n here, and here I have 2/3 plus minus beta times n vertices. Okay. Moreover, in this graph that runs between them, I have a minimum degree condition. So just some very mild one. And for example, it can take something like n/20. So I have this minimum degree condition between the parts. Oh, by the way, I'm only talking about the case here that alpha is equal to 1/3 and not one of these more difficult cases that I addressed in my more difficult theorem. Okay, so I have some minimum degree condition like this, but I also more in addition, I know I can take out a few vertices here and a few vertices there, and the other vertices, they really see almost all on the other side. Yeah? So these here see almost all. And similarly here for these, they also see almost all vertices on the other side. Okay, so we look very close to the extremal graph. And the way that I would now prove my result my result in this case would be that, okay, I would first have to do some kind of step in order to cover these exceptional vertices and also maybe take care of these imbalances here using a few triangles. And then what I'm left with are just these parts here. And moreover, I would kind of arrange myself in such a way that now my ratio would really be that I have 1/3 of the vertices here and 2/3 of the vertices here. Yeah? And because I have my minimum degree condition and also all my vertices see almost all the vertices on the other side, then if I now somehow arbitrarily partition what I'm left with into two sets over here and one set over here, then I can show that this thing here is super regular, this thing is super regular. And of course, now adding my random graph would produce a random bipartite graph over here. Yeah, so that's kind of very roughly the idea of how I would deal with the case that I'm close to extremal. And I just want to make one more remark here. So it could be, the interesting thing, you know, is that it could be that in fact, I have, so I said already these two parts here, I don't need to be precisely of this n/3, n/3 to n/3 sizes, but I could have some less vertices here. So let's say m vertices less over here, and then I would have m vertices more over here. Yeah, and now if I want to do this first step that I mentioned, that I want to kind of get the balance of this object correct, what would that mean? That would mean that I somehow first have to cover these m more vertices that I have over here with triangles alone. Now, because this thing here is smaller, I also know that somehow in here I have some minimum degree of at least m. And therefore, now over here, I'm precisely in this setting that I also said earlier in one of my results, namely that I have a graph with minimum degree m, and I can add some random edges, but then I want to find m disjoint triangles here. Yeah, and so that's exactly why I need this more general result when I want to prove something like this. That's how it comes out. All right. Now, just very briefly, how about the other case? What if I'm non-extremal? Well, here we use the regularity method. So we would apply the regularity lemma to our graph and get some reduced graph out of it. And in this reduced graph, then the first thing we would like to do is to find a matching in this reduced graph. And here what comes in very handy is some stability tool concerning matchings. Now, what does this stability tool concerning matchings do? And by the way, this is inspired by some work of Balog, Muse, and Skokan. Now, what it does is that if I have some minimum degree of the type that I'm interested in, so let's again say alpha is 1/3, then the minimum degree that I'm looking at would be 1/3 minus gamma n, because I'm looking at the reduced graph, and then my reduced graph will have a minimum degree that is a little bit smaller than the graph that I started with. And then I want to find some matching there. And if I'm not close to my extremal graph, as I'm assuming, then I find a matching which is a little bit bigger than what I would usually expect. Yeah, so I get this 4 gamma many more times number of vertices of my reduced graphs, many more edges in my matching. Okay, so I have some matching that I found using this tool. And moreover, I take a matching that is as large as possible. So the remainder of my vertices would form an independent set in my reduced graph. Moreover, it's easy to convince yourself that for any of these matching edges, one of the two ends can see at most one vertex over there. Yeah, so otherwise I would have one edge like this and one edge like this, and then I could get a bigger matching. Okay, so for each of these matching edges, there is one side which sees almost no vertex in the independent set. But that means, because of my minimum degree condition, that my vertices in here, out of these vertices, they have to see really, really many. Yeah? And using this property, I can then find a second matching greedily, eating up all the vertices in this independent set. Okay, and when I did that, is what I have now achieved is I have covered my reduced graph with matching edges and then with some cherries like this. Yeah, so that's one thing that I want to do. And then in a second step, I will use these cherries and my matching edges in order to find, using the random edges, in order to find triangles. And of course, again, there's lots and lots of details that I'm hiding here. So this is the more difficult case. So I have to cover a lot of exceptional vertices. I also have to be really careful when now trying to use these regular pairs together with some random edges to get them covered with triangles, because the probability that I'm now allowed to work with is only C over n. So I don't have this log n over n anymore. I only have probability C over n that I want to work with now. And that really makes the whole job a lot more different. So what we do is we prove a similar embedding result as we did in this case, a similar embedding lemma, but that has to look a bit different because we don't work with this probability anymore. So it will be look a little bit more technical. Okay, but that's roughly the kind of ingredients that go into the proof, and then there's a lot of technical tweaking that we have to do. Okay, good. Now I promised that I would say a little bit about larger cliques. So here again is what is the story for triangle factors. So for triangle factors, we know what the evolution of this perturbed random graphs looks like. And now if I would try to look at the same thing for K4 tilings, again, I get these jumps and I get some more values here. But the first value for alpha, for which we wouldn't know what the answer is, would be alpha is equal to 1/4. Now, what would some reasonable guess be here, what the answer could be? Well, one could be tempted to put here this threshold, which I need in order to get triangles in the purely random graph, right? So that was what I need in order to get a triangle factor in the purely random graph. And similarly to that, when we wanted the triangle factor, that we needed somehow the probability to get a matching, one could ask, yeah, maybe now I just need a triangle factor, so that would be a reasonable guess. And it turns out that this is false. And I will say in a minute a few more things why this is false. But two more words about kind of how false this is. Now it turns out that when the point that this is false is really something that has got to do with these extremal graphs. And one thing that kind of we checked, one can show with some modification of our methods, is that when we are not close to these extremals, that at least at this point here, n over n to the -2/3, so the same answer as here, is the right threshold. Similarly as to what happened here in the non-extremal case, right? And that this here is false is also not some artifact about K4 or about this particular boundary case alpha equal to 1/4, but for kind of other values of R and for other boundary cases, the same thing happens. All right, so now kind of why is this false? How does one see this? That's actually not too difficult. So let's take this probability that we conjectured should be true, and let's also fix some m, which kind of has some mild bounds to them in terms of n. Now what I do is the following. I take, again, a bipartite graph, so A and B, and now A and B are of these sizes. So A is of size n/4, but has a few less vertices than n/4. So minus m, and m was this parameter that I chose here. And these vertices here are added to B. Yeah, so roughly they are of size n/4, 3 n/4, but then we make A a little bit smaller. Now, of course, if I just have this complete bipartite graph, then I won't have the right minimum degree yet, right? So my minimum degree that I want is n/4. But therefore, I just add some copies of KMM over here in the bigger part. So these are all copies of KMM. Right, so now that will mean that I have the correct minimum degree. And And if I want to find the K4 factor in this example here, then what I certainly must have is I must find m copies of my K4s over here purely on this side. Yeah. Now, kind of these graphs that I have here, they are only bipartite, so I somehow need to add some random edges in order to make these m copies of K4 out of that. And now I can just simply use some first moment argument to check whether this is possible. Yeah, and it turns out that now, if you kind of calculate the expectation of the number of K4s that you have over on this bigger side B, then these are not enough. Yeah, so that's really a very simple calculation. Okay, and it turns out you cannot just do this for this particular probability that we first conjectured, but you can actually make your probability a bit smaller, so you can make it sorry, is that smaller, bigger? Bigger. So you can kind of add this polynomial factor here n to the epsilon if you put a bit different bounds on m and make the same first moment calculation go through, right? So the answer for alpha is equal to 1/4 really somehow is now must be somehow different, and we don't know what it should be in the end, what the real answer is in here. So that would be one question that is interesting to look at further. There are some other things that we are further looking at in some ongoing work, and one of these things is universality. So what we were finding were triangle factors, right? So now, of course, you can ask more generally, what about some cycle factors, not for triangles, but maybe for CL? Well, we can do that. We can tell you what is the threshold behavior if you look at CL factors instead. But you could also ask more general about what if I want to look at all graphs with minimum degree 2, and I want my randomly perturbed graph to contain them all at once, which is a little bit of a different question, and that's the question of universality. And that's something that also has been looked at for purely random graphs, and the answer is known, and also for purely extremal graphs, the answer is known. There was some preliminary work by my co-author, Olaf Parczyk, that mainly focused again on the case that alpha is small. So I have a minimum degree graph with a very small linear minimum degree. But the question remained what happens for some bigger minimum degrees. And that's one thing that we answer. And what we say, what our result says is that actually, in fact, the triangle factor is the most difficult graph to get. And once we get the triangle factor, we also get all of these other graphs with maximum degree 2. Okay. More open problems. Well, of course, there is was this original problem of H tilings. So now here I concentrated on KR tilings, and I said, well, even for KR tilings, we don't understand everything yet, but we understand quite a lot. But for more general H tilings, really much less is known. So this is very much open and would be an interesting problem, I think. I just was talking about this 2 universality. One can, of course, now ask the same question for bigger maximum degrees. So for example, 3 universality. So meaning I want to get all graphs with maximum degree 3 simultaneously in my perturbed random graphs. And the question is when would this happen? Again, this is not known and not well understood. It's also a much more difficult question than this 2 universality that I talked about, because this class is much richer. It contains much more graphs, and also it contains expanders, which is something that makes it more difficult. Okay, and that's all that I wanted to mention. Thank you.
Well, thank you very much. Yeah. Let us thank Julia for the nice talk. Questions? Maybe I'll ask a question. So here you talk about 3 universality. So do you believe K4 factor is the hardest one or not?
Yes, I think it should be. Right, so I mean, that's at least for random graphs, that's what happens, right? I mean, that was that's this very recent result which determines the threshold for, is it actually, no, maybe it's not a universality result. Anyway, but so if one doesn't look at the universality question, but just if the question I have all graphs with a maximum degree delta, and I want to know what is the threshold for containing each of them, but maybe not at the same time, but separately. And there, indeed, the KR factor is what is the most difficult to get. And so therefore, I would think that here it should be the same.
Mm-hmm. If I may ask a quick question. Thanks for the very nice talk, Julia. So I was wondering if the following sort of questions have been studied. So one could also think of trying to cover all the edges of my graph by taking the union of H factors of subgraphs that are all isomorphic to H.
Yeah.
So I was wondering if there's any study that's been done on, random graphs where you can, come up with a union of these graphs isomorphic to H covering all the edges, and maybe trying and minimizing the number of such subgraphs required and so on.
Yeah, so I mean that's some packing problem, and I mean there are lots of things have been studied. So certainly we know some things about random graphs. I don't think we understand very well when the random graphs get very sparse. But yeah, I'm not even sure I'm very much up to date with what precisely is known, but since right, so I mean, it's kind of clear why that is. I mean, only recently did we understand these I mean, kind of packing these graphs, even in dense, I mean, even in the complete graph, that's a very recent development that we understand that. but it has certainly been looked at also at in random graphs. I'm not aware that anybody looked at it in these randomly perturbed graphs, but it's a very natural question, yes.
Are there any more questions? If not, let's thank Julia again. I guess this finishes the official part of the talk.